This problem is a limiting reactant problem because the mass of each reactant is provided. We know the mass of N2 is 49.2 kilograms and the mass of H2 is 22.3 kilograms. Now, in order to solve this problem, we start with the 49.2 kilograms of N2 and realize that we're going to be looking for kilograms of NH3. But we're also going to set up a second problem, starting with the 22.3 kilograms of H2, looking for kilograms of NH3. And what we'll do is we'll wind up calculating two different answers, but we wind up selecting the smallest of the two answers because the limiting reactant will determine the amount of product that winds up being produced. So in the first one here, we have kilograms of N2. We take that 49.2 kilograms of N2, and we're going to convert this to moles. And we're actually going to convert it to kilomoles because it turns out if we look at the formula, we have a relationship between grams of N2 and moles of N2. This here is called the molar mass. We go to the periodic table, we see that nitrogen has an atomic mass of 14.01. So if we take that times 2, we wind up with 28.02 grams of N2 for every 1 mole of N2. But now, since we're provided units of kilograms, we should be able to say that there's 28.02 kilograms for every 1 kilomole of N2. At this point, we can set it up as a conversion, placing the 28.02 kilograms of N2 in the denominator, the 1 kilomole of N2 in the numerator. This enables the kilograms of N2 cancel out. Next, we'd like a conversion between the N2 and the NH3. In other words, we want to convert from one substance to another. To convert from one substance to another, we use what's called the molar ratio. And in this case, we would look at the relationship between moles of N2 and moles of NH3. And in this particular setup, we see that the coefficients are 1 and 2. So we'd say for every 1 mole of N2, this would be equivalent to 2 moles of NH3. We can then use this as a conversion factor, placing the 2 moles of NH3 up above and the 1 mole of N2 down below. And if this is the relationship in moles, it will also be the same relationship in units of kilomoles. And so we can simply put a prefix kilo in front, and this then enables us to cancel out these units. Then we have kilomoles of NH3. We're trying to get over to kilograms of NH3. We then need to find the molar mass. In order to find the molar mass, we need a relationship between grams of NH3 and the moles of NH3. Remember once again that the molar mass is the number of grams contained in 1 mole of NH3. So we go to the periodic table, we see that we have 3 hydrogens, each at 1.008. We have 1 nitrogen at 14.01. If we sum them together, we wind up with 17.03 grams of NH3 for every 1 mole. And if we have 17.03 grams in 1 mole, that's the same as saying we have 17.03 kilograms in every 1 kilomole. We can then substitute that into the problem. We'd put the 1 kilomole of NH3 down below. We'd put the 17.03 kilograms of NH3 up above. Units cancel out. Next, we start with the 22.3 kilograms of H2. Now the first step here is we need to take the mass of H2 and convert it to moles. If we look at the periodic table, we see that the atomic mass for hydrogen is 1.008. If we take that times 2, we get 2.016 grams of hydrogen for every 1 mole of hydrogen. But since we have units of kilograms, we could say that this is also the number of kilograms for every 1 kilomole. Placing it into the setup would put the 2.016 kilograms of H2 down below and the 1 kilomole of H2 up above. This enables us to cancel out units of kilograms of H2. Next, we need a conversion that takes us from H2 over to NH3, and that conversion is the molar ratio. And if we look at this particular molar ratio, we'd see that there are 3 moles of H2 for every 2 moles of NH3. And again, these two are equivalent to each other, but this would be the same as saying that there are 3 kilomoles of H2 for every 2 kilomoles of NH3. We put the 3 kilomoles of H2 down below. We put the 2 kilomoles of NH3 up above. And once again, we wind up having units of kilomoles of H2 cancel out. At this point then, we need one more conversion. We use the same conversion that we have above, and that is we have 17.03 kilograms of NH3 for every 1 kilomole of NH3. And the kilomoles of NH3 cancel out. We then go to our calculator, we multiply everything through. We have 49.2, multiply that by 2, and again by 17.03. We divide that result by 28.02, and we wind up with an answer of 59.8, and that would be kilograms of NH3. On the second one, we take 22.3, we multiply that by 2, and again by 17.03. We divide that result by 2.016, and we divide it again by 3. Upon doing so, we wind up with an answer of 126 kilograms of NH3. Of course, now we have two different answers. Looks like we go with the first answer, because what this implies is that once we get up to 59.8 kilograms of NH3, we run out of N2, meaning that the nitrogen here is the limiting reactant. And so again, for the answer number 1, that answer for the first one would be 59.3 kilograms of NH3. For the second one now, we want to calculate the percent yield if 52.6 kilograms of NH3 were actually produced. Now, to calculate the percentage yield, we remember that in general, percentages are equal to the part over the whole times 100. And this means that if we're looking at a percentage yield, we would take the actual yield, we divide that actual yield by the theoretical yield, and then we take that result and multiply by 100. At this point then, we would take the actual yield, which in this case is the 52.6 kilograms of NH3. We divide it by the theoretical yield, which is the 59.8 kilograms of NH3. We take that result, multiply by 100. What happens here now is that the kilograms of NH3 cancel out. We take the 52.6, divide it by 59.8, take that result, multiply by 100, and we wind up with a resulting answer of, that appears to be 88.0 yield. Earlier on, we found out that nitrogen was the limiting reactant. Now, if nitrogen is the limiting reactant, that means that hydrogen is the excess reactant, and we'd like to know then what mass of this reactant remains unconsumed. Well, what we know then is that if the nitrogen is the limiting reactant, we know that the 49.2 kilograms of N2 reacted. And so if this reacted, we should be able to find out the mass of the hydrogen that reacted as well. So with this here, we go ahead and take our kilograms of N2 and we convert this to kilimoles. We found out that for every 1 kilomole of N2, we have 28.02 kilograms of N2. Kilograms of N2 cancel out. Then we want to get from N2 over to H2. Looking at the balanced chemical equation, we see that there's 1 mole of N2 for every 3 moles of H2. So placing this in here, we put the 1 mole of N2 down below, the 3 moles of H2 up above. Of course, now, in order to get the units to cancel, we multiply the numerator and denominator by 1,000 to get kilomoles of H2 and kilomoles of N2. This means that kilomoles of N2 will cancel out. And next we need to get over to kilograms of H2. And we found out up above here that 2.01 kilograms of H2 are present in every 1 kilomole of H2, and the units of kilomoles of H2 will cancel out. At this point then, we should be able to multiply it through and calculate an answer. We do that by taking 49.2, multiplying that by 3, and again by 2.016, and dividing that result by 28.02. And upon doing so, we wind up with an answer of 10.6. So again, we have 10.6, and that'd be kilograms of H2. Well, then we need to remember that this is the kilograms of N2 that reacted. So this must be the kilograms of H2 that reacted as well. We know the mass of H2 that we started with, which is the 22.3. Check again, there we go. So again, we started with 22.3 kilograms of H2 at the start. We know that 10.6 kilograms of the H2 reacted. And so if we subtract these, we wind up with 11.7 kilograms of H2. And this is the amount here then that remains. And that then would be the answer that we wind up recording, saying that 11.7 kilograms of H2 remain unconsumed. And there are the 3 answers.